All right, class. In this video, we are going to cover the preparation of an epoxide. So remember, so what is an epoxide? So an epoxide is a special kind of ether. It's a cyclic ether where where the ring is a three-membered ring. And recall that we can form these from the epoxidation of an alkene with a peroxy acid. The most common peroxy acid that we use are MCPBA, metachloroperoxybenzoic acid, or peroxyacetic acid. These are the two most common peroxy acids that we use. So when you take this molecule when you take an alkene and you react it with this peroxy acid, remember it's a syn addition and it's a cyclic transition state. And if you had to think about it, like which of these oxygens is when you have this bond here, this bond is weak. It makes one of these oxygens kind of more electropositive than the other one. And the way this works is that this oxygen is kind of more electropositive than this oxygen here. So, and I'm going to redraw this in such a way to kind of show you how this, to kind of jog your memory of how this works. So it's proposed to go by this kind of cyclic transition state here, where the double bond attacks the more electropositive oxygen, the more electrophilic oxygen. That breaks the weak oxygen-oxygen bond. That will then cause these electrons to go over to make a CO double bond here. That pushes a pair of electrons in this other CO double bond to pull that proton off. Then these electrons in that oxygen-hydrogen bond are going to go and attack the carbocation that's forming on the opposite carbon. So while one carbon is forming a bond with the oxygen, that carbon's becoming partially positive. That gets attacked by these electrons here. All of this happens at once, so it's a syn addition. So the ring is facing one side. Okay. So because of this syn addition, these reactions are stereospecific. You can see this stereospecificity really easily in these cyclic systems. This is also still stereospecific in acyclic systems. So notice that when you do the epoxidation of the cis alkene here, the R groups, they end up on the same side of the three-membered ring. If you start with the trans alkene, the R groups end up on opposite sides of the epoxide there. Another way to form epoxides is from the halohydrin. So remember, the halohydrin, this molecule comes from the reaction of an alkene with a halogen in the presence of water as the solvent. And notice that this is a trans addition of these two groups. And so when you have these two groups right here, you can take the halohydrin and react it with sodium hydroxide. And if you do that, what's going to happen here is that the sodium hydroxide can deprotonate the alcohol here, so that you're doing a proton transfer. You're basically kind of taking the negative charge from this oxygen and making this oxygen negatively charged. So there's a proton transfer. The hydroxide removes the proton on the alcohol to make the alkoxide here. Because the alkoxide is in close proximity to this alkyl halide, it can just slam down via an intramolecular. So intramolecular again means this happens internally, an intramolecular SN2 reaction to make the epoxide. Notice that the bromine and the alkoxide have to be trans to each other, opposite of each other in this bond here. They have to have this anti-periplanar relationship in order for this reaction to work. So that's how we make epoxides. Let me know if you have any questions. Thanks for watching, and I will talk to you later.